We are now in this section of the course, section 2. We are going to talk about magnetic resonance imaging, and as you will see, this is distinctly different from the X-ray based techniques that we have discussed in part 1. And I want to start now the introducing of the magnetic resonance of MRI. I want to start out with first some examples, and we'll start with examples of animal models. This is a high-resolution scan, MRI scan of a mouse. It's a whole body scan at very high resolution, and you can certainly appreciate all the fine details that are observable here in this, particularly in the soft tissue. Here is another example of blood vessels. So here contrast agents were used that depict the vast blood vessel here in this mouse embryo. Another example here is brain function. We're looking at the vasculature, blood vessels inside the brain. Here's the brain, here's another brain scan, and looking at the activity in the brain tissue that can also be done with MRI. Here's an example of a longitudinal study looking at a stroke in the brain, the development of the stroke. One can see some bright area here. And this is the Nissl staining that shows the death of neurons. That's done after the MRI scanning has been done. And finally, another example is that one can look at chemical compounds here, phosphorus, phosphocreatine ATP, using spectroscopy of, in this case, the rat brain. One thing, and this is really an important message here, is one thing that distinguishes MRI from the previous modalities, the other modalities, is it has one instrument, one magnet, but basically it has many modalities built into it, or as we would call it, many different contrast mechanisms. Let me illustrate this with the human brain. We have here a contrast mechanism exploited that's called FLAIR. It highlights certain processes, typically for multiple sclerosis. Then we have here contrast agent application. We have here an image of cerebral blood volume changes. We have a mechanism called MTR, that's magnetization transfer ratio imaging. We have diffusion, apparent diffusion coefficient, or ADC, that's being measured here. This is all the same patient. And finally, we have a biochemical measurement of choline to N-acetyl aspartate concentrations, a map showing changes here always in the same lesion. So if we take this this has been all done on the same patient, pretty much in the same session, and we're obtaining 6 different views of the same process that's going on. And this is exploiting the same principle, the same detection principle, the same instrumentation principle, but there are many ways in which one can manipulate the contrast with MRI, and therefore what is important to be stressed here, what I like to stress here, is we have one magnet, many modalities. We don't have an MRI as such. An MRI as such does not exist. An MRI comes always with a definition of what particular contrast mechanism is being imaged. Let me go on with the example of one magnet, many contrasts in the rat brain. We have phase imaging, so we have a normal image here, this traditional image, and if one looks at the magnetic field within the tissue, one can see the different cortical layers inside the brain. We can look at the distribution of glutamate, which is the major excitatory neurotransmitter in the brain. One can look at transport of calcium by means of a tracer. In this case, it's manganese. This is in response to activation, showing high activity in cortical layer 3 and 4 upon a stimulation, upon a specific task. Or here is finally an example of quantifying cerebral blood flow in the brain using a technique called arterial spin labeling. This is in an animal with anesthetized with alpha chloralose. This is a normal animal, and this is an animal subjected to hypoglycemia, that is low blood sugars. So also here, not only in the human brain, but also in the animal brain, we have many different contrasts that we can obtain, all with the same scanner and different depictions of what is going on. And these are just the examples for the brain. This, of course, holds true for all the other organs as well. So then, what are the essential components of an MRI scanner? And I want to give out here a scheme that gives you an idea what's inside an MRI scanner, and I will also highlight the aspects of the MRI scanner that we're going to deal with in this series of lectures. So here's a typical MRI scanner, again covered in a nice cover. Patients don't want to see the physics or the engineering, and this is when you enter the magnet room, as a patient, what you would typically see. So what is inside the scanner? We have inside the scanner, we have a magnet. It's magnetic resonance, so there's a big magnet inside the scanner. That's inside here. You're going inside the magnet. Inside the magnet we have gradient coils, RF coils, the patient table we can see here. This is the equivalent of this scanner for animal scans here. So here's a smaller opening, as we've seen with all the other imaging techniques. When it comes to small animal imaging, rodent imaging, the dimensions of the scanner are being reduced, at least in terms of the hole. So we have the magnet, which is here, and this is the magnet here. We have the gradient coils. They are inside the cover. We will not see them as patients. They would be here. And we have the radio frequency coil, which is this thing here, that pretty much looks like a bird cage lying flat, and it's actually called a bird cage. If we take a magnet, we take the cover away, then the cut, if we look at the open cut, then we can see quite a bit of engineering and physics behind this, a lot of copper, etc. That is the magnet. When you cut it open, we don't see the magnet yet, we just see the inside, so that's the gradient coil system here. So if we take the entire system, we plot it out, and we look at all the components, then we see lots of different components that are important in making a scanner operate, and yes, it is a complex machine. However, we will not focus on all the aspects of what's involved in running an MRI scanner. We'll touch upon them where necessary to understand a few of the consequences, but we'll not go into every detail. What we will focus on is the major elements of MRI, and that is the nucleus. We'll focus on the magnet, we'll focus on the RF coil, and we'll focus on the gradient coil. Those are the elements of the scanner that we're going to focus on. All the rest here, the addition, the important engineering, will not go into much detail for the purpose of understanding the fundamentals of MRI. Now, one thing is with an MRI is it is a magnet, and that magnet is typically, in practice, always on. It is typically cooled by superconducting wires that are cooled to liquid helium temperature, so 4 Kelvin. So it's cold inside there, and the current will stay in there for 1,000 years. As it is superconducting, the resistance of the wires is essentially 0, so the current will stay in there and the magnet is never being off. So what are we looking at here? What kind of magnetic fields? And we'll use here the magnetic field generated by the MRI magnet. The unit here is Tesla. The Earth's magnetic field is roughly 5 × 10⁻⁵ Tesla. That's the magnetic field we're all constantly experiencing. Electromagnets, so you take just a copper wire, wind it like this, run a current through it. You can produce such magnets, but they will have a limit of magnetic field strength that is, for imaging purposes, typically below 1.5 Tesla. For MRI, what we are looking at is magnetic field strengths in the range of 1 to 7 Tesla. So, and this has a consequence. We have a powerful magnet. It is superconducting, so this powerful magnet is always on. We cannot come into the room and quickly turn it off, unlike a CT scanner where we can turn off the X-ray tube and we won't have radioactivity being produced. For PET and SPECT scanner, if we don't have tracers in our bodies, we're not exposed to any radioactivity. But if you enter into a room with an MRI magnet, you are entering a powerful magnet, and this requires some precautions that I want to discuss. Illustrate now that one has to be cautious around the magnet. You can smell the magnetic field, you can't necessarily feel it, and so it can have some surprises in the observation when being around the magnet without the necessary precautions. And that just explains why we are asking subjects or visitors that come close to the magnets to take some extra precautions. So let's look at this example here. In this video, what you're seeing is an aluminum block that's placed in front of the magnet on the patient bed. As the aluminum block is tipped over, it falls over. If you now look at the aluminum block placed inside the magnet or close to the magnet, so inside the magnetic field, and as the aluminum block is tipped over, it falls very slowly. What is happening here is that as the aluminum block falls, changes orientation, the magnetic flux in the aluminum changes. So we have Faraday's law of induction. So there are, because the magnetic field orientation in across that block is changing, we have induced currents. These induced currents are producing themselves a magnetic field that counteracts the main magnetic field, and so this produces a reduced a force that opposes the motion of the magnet. This principle is used in electromagnetic braking, for example, in the more modern hybrid cars when we brake without using the physical contact, or in electrical trains. Now here in this example, what is being done here is a tennis ball filled with nails. Nails are ferromagnetic, so they're attracted by the magnetic field, and the person is letting go of this tennis ball filled with ferromagnetic nails, and it goes tung tung tung, goes into the scanner and then sticks to the side. What is happening here is the more critical effect, and that is we have a ferromagnetic iron object that is exposed to a change in magnetic field. So if we have a difference in magnetic field across that object, and therefore it exerts a force on the object, and that object is being attracted such that it ultimately enters into the scanner. The last example, the next example is a video surveillance camera of a friend of mine who posted it on his YouTube channel. So you see the two gentlemen here, they've been asked to enter into the magnet room and put up a support structure, a frame for putting some shelves, so one can put blankets and cushions, etc. into the room. Notice the one person who has in his hands has a battery operated drill, so they obviously wants to do some drilling on this structure or tightening some screws. As we are watching this video, you might notice at a certain time point that he is now without the drill, and as you're observing the two gentlemen, they are now looking inside the magnet. So what has happened? Well, the drill has most likely some ferromagnetic components to it, or at least a battery. Batteries are typically ferromagnetic. And as he was moving around in the room, he wasn't paying attention to the magnet that is in the back of the room, and as he got too close to the magnet, the magnetic field attracted the drill. He could no longer hold to it, and it flew inside the magnet. In this case, there was nothing of major consequence happening. The drill was removed, and aside from the scare, nothing happened. However, this is, in the context of medical application, is a far more serious issue. And here's an illustration of an experiment showing the same effect with a gas bottle. Just an ordinary gas bottle, oxygen bottle. You have lots of oxygen bottles in the hospital. They're placing this bottle on the patient bed. And as you can see on the patient bed, instead of putting a patient, they're putting a watermelon as our subject inside the RF coil where the head would be. The experiment that was here done is to illustrate what happens if a magnetic object that's being put too close to the magnet, when it starts to get attracted by the magnet, what then happens? Obviously, when it gets closer, as we've seen with the drill or the nail-filled ball, as it gets close to the magnet, the difference in magnetic field creates a net force on the object. The force, and as we see in this demonstration, accelerates this gas bottle. It accelerates it towards the watermelon. It has the impact on the watermelon, and the watermelon is being crushed. We see this at the end of the video where they go to the back of the magnet and they show how much this watermelon has been crushed. So extreme caution is necessary with ferromagnetic objects, and this is particularly difficult in the medical context. This happened in the beginning of this millennium in the state of New York, that a subject, a cancer patient, was being, for control purposes, being scanned. A nurse heard the word oxygen bottle, went into the hallway, grabbed the oxygen bottle, walked with the oxygen bottle into the room. The oxygen bottle got attracted, and unfortunately for the subject was still in the magnet, and that created, of course, a unfortunate death of this subject. The difficulty here is, as medical professionals are trained to react to emergency situations, they are not all trained to work and live around the magnet. And so the first response is to help the patient. And so, yes, you grab the oxygen bottle, you run into the room, and the oxygen bottle is being attracted. That's the situation here. It requires specific measures. The measures are to take off all magnetic things that we carry on ourselves, and in the case of a medical emergency in a MR scanner, what one would do is actually, the first reaction is to take the subject out of the magnet and out of the magnet room, and then only start coming in with medical equipment. CPR is obviously fine, but one has to be extremely vigilant, because we do not feel, we do not smell, we do not see the magnetic field. So to give you an illustration, here's an example of a magnet with a chair attached to it, and this chair has obviously a lot of ferromagnetic material, and you can see the quite considerable effort that it takes to remove that chair. That's been, it's a chair with wheels on it, so it somehow got too close to the magnet, was suddenly attracted, and bang, it went into the magnet. And you can appreciate from the forces, the effort that's being done, how strong these forces are on the chair. And obviously, once one is away where the magnetic field doesn't vary a lot, then this force is being substantially reduced, and we have less to consider. It really is a matter of the vicinity of the magnet where the magnetic field changes very strongly. So this is a danger of magnetic MRI scanners. It's not a biological risk, it's a danger. It's just like walking up and down the stairs. If you don't pay attention, you can fall and break your neck. Here we have to be around the magnet. We have to be cautious with making sure that ferromagnetic objects stay far away from our subject and from the scanner, and then we are okay. Another issue that I want to address, it is of some historical interest, especially with the perspective of Europe, but the question is, let's say we forget about ferromagnetic objects and we're just ourselves walking around the magnet. And the question is, what kind of exposures of magnetic field changes can we subject ourselves to? And I want to make here the example by comparison comparing the effects that we see with transcranial magnetic stimulation. Transcranial magnetic stimulation is a technique used in neuroscience to investigate the functioning of certain brain areas. It is allowed in healthy volunteers, and these pulses are applied quite frequently. So I want to relate what we are, if we move around the magnet, what this means in relation to TMS. So here's the TMS scanner. Here's the coil that produces the magnetic field, the subject here. And what is being done is one produces a magnetic field, B0, with this coil that goes from 0 to 2 Tesla in roughly 100 microseconds. So if we take a conservative estimate, this amounts to 20,000 Tesla per second change in magnetic field, dB dt. Now, what I want to do with this calculation is just to get an idea. To produce a similar change in magnetic field, how fast would we have to walk to a 7 Tesla scanner over a distance of 1.4 meters? We'll assume we go over 1.4 meters from 0 to 7 Tesla, and we want to expose ourselves to the same change of magnetic field per time. So we have a change in magnetic field per distance, which is 5 Tesla per meter. We have 7 divided by 1.4, so this gives us 5 Teslas per meter. And we want to now have a change in magnetic field per time, so that's velocity over distance. That gives us per time times the change in magnetic field. We want this to be 20,000 Tesla per second. And we can solve this, so we can calculate what velocity would we need to produce a magnetic field change of 20,000 Teslas per second. And the calculation here, as you can easily verify, produces a velocity of 4,000 meters per second or 14,000 kilometers per hour. This is essentially 10 times the Earth's rotational speed. That's a tremendous velocity. Now, this is very crude, and it's by no means meant to be correct, but let's go a little bit into finer details, and we'll look at Faraday's law in more detail. We have Faraday's law, which says the induced voltage is equals to the area times the change in magnetic field per time. So we're obviously having, with the transcranial magnetic stimulation, we're not having the same area exposed to the magnetic field as we have with our body as we run towards the magnet. So we'll correct for the surface area. The TMS coil with a radius of 5 centimeters, we can calculate an area of 0.008 meters squared. And we'll estimate that the upper trunk, my upper trunk here, is roughly a half a square meter of surface area. We'll correct that. And then we are getting, for correcting for the fact that our area is bigger than the area of the TMS coil, to have the same induced voltage in our body, we're obtaining a velocity of 63 meters per second, or 220 kilometers per hour. So if we run towards the magnet and we go from 0 to 7 Tesla over a distance of 1.4 meters, we are going to be exposed in the upper trunk to voltages that correspond to those that we are exposed to in the brain with TMS at 220 kilometers per hour. Now, what we have to consider is, for most modern magnets, most of the static magnetic field is actually within the bore of the magnet, that is within the structure. So we actually, if we are on the outside, we can't even expose ourselves to the full 7 Tesla. So we don't, that means also most of the change is happening in there. We don't start at 0 Tesla, we don't end at 7 Tesla. We have also the fact that the distance is more like 7 meters over which we approach the magnet and not 1.4 meters. So if we actually wanted to expose ourselves to the same effect around a magnetic field, then the equivalent speed to produce the same voltages as we have with TMS would be several fold higher than the 220 kilometers per hour. And let's be honest, in reality, our speed is going to be already 2 orders of magnitude lower than what is here. So it is my opinion here that the considerations about motion around a static magnetic field, around an MRI scanner are so low, the induced voltages is that are well beyond any concern that we should have and are having.